The O'Neill cylinder is the most thoroughly designed home humanity has ever planned to build, and the wall that holds it together must withstand a force that exceeds the breaking point of every material we have ever manufactured at a scale we have never come close to producing, with zero tolerance for the imperfections that exist in every real structure ever built. That sentence was written by the people who did the math. Not critics, not outsiders, the engineers who spent years refining the blueprint. They wrote it down, published it, and then the popular version of this story left it out. The cylinder exists in more serious long-term space colonization literature than any other concept. It shows up in NASA study reports, in university curricula, in the stated goals of people who have actually built rockets. It is not science fiction. It is a calculated proposal from a Princeton physicist named Gerard O'Neill, who ran the numbers in 1974 and concluded that building human habitats in space was not only possible, but practical. Practical in a specific engineering sense, meaning the forces involved were understood, the material requirements were defined, and the structure would hold. He was right that the forces were understood. He was right that the material requirements were defined. The wall is the part that has not moved. Picture the structure before the problem arrives. A cylinder 8 kilometers wide and roughly 30 kilometers long, spinning slowly in space. Not dramatically fast, just fast enough that the inside of the cylinder wall behaves like a floor. You walk on it. Above you is the other side of the cylinder, covered with landscape, forests, rivers. Cities built on the inner surface of a tube with a circumference longer than a marathon course. The sky is curved. Weather happens, crops grow. There are 50 kilometers of continuous structure wrapped around air, water, soil, and everything living in it. And it is spinning, and the spin is the only thing between the people inside and the vacuum outside. The wall of that cylinder is doing something specific and unrelenting. Every kilogram of soil pressing outward against it. Every liter of water in every river and lake pressing outward against it. Every building, every road, every person, every breath of atmosphere pressing outward against it. The rotation that generates the gravity does not pull inward. It pushes everything outward constantly, at the same rate, and the wall absorbs that push across its entire surface, everywhere at once, in every direction around the circumference. That push has a name engineers use: hoop stress. Imagine wrapping a rubber band around an inflating balloon. The rubber band wants to tear itself apart in a ring. The force trying to split the rubber band, that continuous tension pulling the ring open, is hoop stress. Now make the balloon 8 kilometers wide. Fill it with soil 20 meters deep. Add lakes. Add a full atmosphere. Make it spin. The hoop stress in the wall of that cylinder reaches a number that has a specific value, and that value has a ceiling. And the ceiling is the breaking point of the material the wall is made from. Steel fails at around 500 million pascals of tensile stress, the precise point at which a steel structure, pulled from both ends, tears. 1 pascal is roughly the pressure of a dollar bill resting flat on your palm. 500 million of them applied to every point in the steel simultaneously in a pulling direction is the last number steel ever sees. For the O'Neill cylinder at full design dimensions, the hoop stress in the wall exceeds that number by a factor of several times over. Not close, not marginal, over. Steel is not a candidate. Titanium is not a candidate. Kevlar, the material used in body armor and bulletproof glass, is not a candidate. Every structural material humanity manufactures at industrial scale fails before the stress the cylinder wall must carry, and the cylinder has not been hit by anything, has not been damaged, has not aged. It just spun up. The physics of operating it is already tearing it apart. That leaves one obvious answer. The viewer thinking clearly already has it: carbon nanotubes. The logic is not wrong on its face. Carbon nanotubes are the strongest material ever measured in a laboratory setting. Individual nanotube fibers, tested in controlled conditions, exhibit tensile strength that exceeds steel by factors of 10 or more. The reasoning feels like a pattern that has already worked. Wood gave way to iron, iron to steel, steel to advanced alloys and composites to carbon fiber. The next step is nanotubes, and the problem dissolves. Engineers get stronger materials. Engineers always have. Why would this be different? The measurement is real. In a laboratory, with a nanotube fiber a fraction of a millimeter long, the number holds. The fiber pulls to extraordinary strength before it breaks. Every physics textbook that lists the property is reporting an accurate measurement. The problem is not that the number was invented. The problem is what happens to that number when you stop measuring a microscopic fiber in a controlled environment and start building a wall 50 kilometers around. A real manufactured structure is not a laboratory sample. It is not a single fiber. It is billions of fibers bonded together, aligned, attached at joints, processed at temperatures that subtly alter their molecular structure, assembled by machines that introduce microscopic variations in density and orientation, and delivered to a construction site where every connection point between sections becomes a stress concentrator, a location where force does not distribute evenly, but instead multiplies locally. In the real world, the gap between what a material does in a laboratory test and what it does at construction scale is not a small engineering detail. It is a factor of 2 to 5 reduction in effective strength. Carbon fiber composites, the best nanotube-adjacent material currently manufacturable at scale, achieve practical tensile strength of around 3,500 million pascals in real structural applications. That number sits at the low edge of viability for reduced radius designs, not the full-scale O'Neill. And you have no margin left for imperfection. The imperfections are not optional, they are physical. Every weld point in a structure concentrates stress. Every joint between wall sections concentrates stress. Every micrometeorite impact scar and a cylinder operating in deep space for decades accumulates thousands, concentrates stress. Every thermal cycle as the cylinder passes in and out of sunlight slightly expands and contracts the wall material. Fatigue that after 10 years of continuous rotation has visited every point on that wall hundreds of millions of times. Each of those visits removes a small amount of residual material strength. A material that barely clears the hoop stress threshold on day 1 does not clear it on year 15. The wall that was marginally holding is now marginally failing, and the failure begins at whichever imperfection has accumulated the most stress concentration over the operational lifetime. That moment, the initiation point, is where the physics stops being an engineering concern and becomes a countdown. A crack in a hoop-stressed wall does not grow slowly. It does not give a warning. It propagates around the circumference at the speed of a pressure wave moving through the material wall, which is fast enough that the crack travels the full 50-kilometer circumference in seconds. There's no sensor network that detects it before it has already traveled 10 kilometers. There's no repair crew that intercepts it. There is no partial failure. You are standing inside that cylinder, and in the time it takes to say one sentence aloud, the wall that wraps around your entire world unzips from one end to the other. The atmospheric pressure inside, the same pressure that makes the habitat breathable, is now driving explosive decompression through that tear, with the force of everything above zero pressing outward through a gap that is growing at the speed of sound. The soil layer, the water in the rivers, the structural foundations of every building, everything that the wall was holding in place against the centrifugal effect of the rotation is now moving outward through the breach or collapsing inward as the pressure differential reverses. The end caps, The circular walls that seal both ends of the cylinder are now absorbing the asymmetric load of a structure whose primary wall has failed. They were not designed for that load. They were designed for a wall that was intact. They follow the primary failure within seconds, not minutes. And the rotating debris field that was a habitat is now an expanding cloud of material in space, with no rescue vehicle, no nearby structure, no survivable partial outcome for anyone inside. You do not need to imagine the scale of what is lost. Just the number is enough. 50 kilometers of wall, unzipped in seconds, and every person who had a window to look out of is now part of the debris. In the summer of 1975, a group of engineers, physicists, and researchers gathered at Stanford University under a NASA study program specifically convened to evaluate O'Neill's cylinder concept in technical detail. The study ran for 10 weeks. The participants produced a report that is still cited today as the most rigorous early technical analysis of the habitat. They confirmed the basic physics of the rotating habitat. They confirmed the viability of the artificial gravity mechanism. They confirmed that the interior design, the agriculture, the atmospheric management, and the energy systems was technically coherent. And in the structural section, they wrote down the problem without softening it. The material requirement for the largest proposed designs exceeded the tensile strength of any substance then available. They identified advanced carbon-based composites and structural fibers as the necessary development path. They noted that this development was unconfirmed and that the concept depended on a material property that had not yet been demonstrated in any manufacturable form. That was 1975. The flag is still there. It has not been cleared. The same report that confirmed the concept also confirmed the wall, and the wall has not moved in 50 years of material science development. The people who ran that study were not pessimists. They were engineers who did what engineers do. They identified the gap between what the design requires and what the physical world currently provides. The gap in 1975 was a specific number. The gap today is a smaller number. It is still a gap. The best manufacturable structural material available in 2024 achieves practical tensile strength at the low edge of viability for designs smaller than the original specifications, with no safety margin for imperfection, and no nanotube composite process currently exists that produces the consistent, defect-free, large-scale structural performance that a cylinder wall requires. That is not a funding problem. That is not a political will problem. That is a physics problem, and physics does not negotiate. The deepest irony in the O'Neill cylinder is precise enough to state in a single sentence. The variable that makes the habitat feel like a world is the same variable that tears it apart: radius. A small cylinder, a few hundred meters across, can be built from materials that exist. It produces an environment that feels like the inside of a pipe. The spin is perceptible as a physical sensation. The curvature of the floor is visible to the naked eye. The sky does not look like a sky. It looks like the opposite wall of a room, and there is no horizon. And the psychological space of living there is nothing like the open landscape that makes the original concept feel like a home. Every design decision that increases the radius to eliminate those problems, to push the curvature below the threshold of perception, to give the interior enough surface area for genuine weather, for clouds that do not touch the ground, for a horizon that sits at a believable distance, every one of those decisions scales the hoop stress upward at the same rate. The cylinder that feels like a world fails. The cylinder that holds together feels like a tube. There is no radius at which both statements are false simultaneously. That constraint does not expire. It is not waiting for a manufacturing breakthrough to uncover new physics. The relationship between rotation, radius, mass, and wall stress is geometry. It does not change with better equipment. a civilization 10,000 years more advanced than ours, attempting to build the O'Neill cylinder at full specifications, faces the same equation. The question it cannot yet answer is whether any stable form of matter has the tensile strength the design requires, at the scale the design requires it. Not whether engineers are clever enough, whether the periodic table cooperates. Every modular rotating habitat currently under serious engineering discussion, the designs that do not appear in popular space colonization roadmaps because they are smaller and less spectacular, is a version of the same answer. Shrink the radius until the wall holds and live with what that costs you. Those proposals are real. Some of them are buildable for materials that exist today. None of them are the O'Neill cylinder. They are structures that chose survivability over the vision, and the vision is what every serious long-term space colonization plan still uses in its slide decks. The blueprint is complete. It has been complete since 1974. The wall is not. And every mission architecture that treats permanent large-scale space habitation as the end goal, Artemis, long-duration Mars colonization, any crude structure beyond low Earth orbit designed for generational occupation eventually arrives at the same room with the same flag on the same whiteboard, and the question written underneath it has not changed. What do you build the wall from, and how do you confirm it holds before 50,000 people are living inside it?